Hello, this is Stat134, Lecture 9. You have a Quiz 2 on Monday covering Chapter 2, Sections 2.1, 2.2, 2.4, and 2.5. Last time we finished Chapter 2, and here is an overview. We have the hypergeometric distribution with parameters capital N, capital G, and N. Capital N being the population size, capital G being the successes or good elements in that population, and small n being the sample size. We can approximate the hypergeometric by the binomial when capital N, your population size, is large, because then sampling with and without replacement are about the same. And then the probability of being good in your population is capital G over capital N. Binomial NP can also be approximated by Poisson when P goes to 0, N goes to infinity, and NP goes to a number mu. And here mu minus 3 sigma has to be less than 0, where mu is n times p and sigma is square root of npq, where q is 1 minus p. This gives us Poisson, and it can also be approximated by the normal distribution, where when n, your sample size, is large, that follows from the central limit theorem that we'll cover in Chapter 4. Mu is np and sigma is square root of npq. And here, mu plus or minus 3 sigma is between 0 and n. When we're approximating a discrete distribution, such as the binomial, by a continuous distribution, such as the normal, we need a continuity correction. Today we covered section 3.1 concerning random variables, the joint distribution of two random variables, and the distribution of the sum of two random variables. So a random variable is the outcome of an experiment. So for example, if you flip a probability P coin twice, X is the number of heads. So when you write X equals 1, that is an event. And the probability that X is 1 just follows the binomial formula. We write X tilde bin 2P to mean that X belongs to the binomial distribution, or X has the same distribution as the binomial distribution, with N is 2 and P is whatever P is. So more precisely, X is a function from your outcome space to the real numbers. So in this case, our outcome space are head, 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 tail, tail, head, tail, tail. And to each of these outcomes, we associated the number of heads in that outcome. So X equals 1 means a subset of all the outcomes, in particular head, tail, tail, heads. So we can write the probability distribution for X by making such a table, and it is 1/4, 1/2, 1/4. And if G is a function of X, so for example, the absolute value of X minus 1, you see then that the values of this function of X are 0 and 1, and you can find the distribution of G of X to be 1/2, 1/2. You can see here that when it has the value 0, that we have probability of 1/4 and 1/4, because this corresponds to the head, head, tail, tail situation. and otherwise we have head, tail, tail, head. So that's also probability 1/2. The joint distribution xy is the joint outcome of two random variables, x and y. So when we write the event x equals little x, y equals little y, this is the intersection of the event x equals x and y equals y. So we are assuming here we have some common outcome space. So x, for example, is that you're making one draw from this box here containing 4 tickets, and given that x is little x, y is the number of heads in x coin tosses. So the probability that x is 1, y is 1, because the way this problem is laid out, we have a sequence of steps here. You pick from the box, and the number that you get is the number of times you flip a coin and determine the number of heads. So it's natural then to use the multiplication rule to find the probability of this intersection. And the multiplication rule says that it's the conditional probability followed by the unconditional probability. And so we can find each of these and find that the probability of drawing 1 and getting 1 head is 1/8. So another example, a fair coin is tossed twice. Let x be the number of heads on the first toss, y the number of heads on the first 2 tosses. Clearly x and y are dependent here. We can write out the joint distribution as a table now, where I've written x, the values of x on the bottom increasing, the values of y on the side increasing from bottom to top. And I've written on the opposite end of the table the marginal probabilities for x and y, which now the marginal probabilities are the marginal x's are the sum of the columns. So in other words, your probability of x, where you take the joint probabilities and you just add up all of the for a given x, you sum through all the y values. So then you guys figured out the values for this table are as shown here. So you can see from the marginal probabilities that x is binomial 1 1/2, because the marginal for x is 1/2 1/2, and y is binomial 2 1/2, because the marginal probability for y has a distribution 1/4 1/2 1/4. So the conditional probability of y is 0 given that x is 0, what is that? Well, y is 0, x is 0, so that is this cell here. Maybe I'll just do this in blue. So this cell here, okay. So you can just reason that out. So what the meaning of that is that the first, given that the first is a tail, the chance that the first 2 are tails. So what would that be? Well, so using Bayes' rule, that is the probability that the first 2 are tails divided by the probability that the first is a tail. So that's 1/4 over 1/2, which is 1/2. And Similarly, you can find the probability that y is 0 given x is 1, so that turns out to be 0. Now, the fact that these aren't the same value tells you that that the probability of y depends on x, and hence y must be dependent on x, which makes sense here, right? So we say that two random variables are independent if the conditional probability is actually an unconditional probability. In other words, there's no dependence on x for all values of x and x and y and y. Now, by the multiplication rule, if x and y are independent, then you can write this factorization. The probability that x is x and y is the probability that x is x times the probability that y is y. So then we did a concept test where I gave you this joint distribution table and asked you, are x and y independent? Are these conditional probabilities equal? Is more than one of the above true? Are none of the above true? And after some discussion, many of you realized that A and B are both true. So to see that x and y are independent, all you need to do is for each marginal, so you just want to show that each cell, so for example, this cell here is coming from the product of these from these two marginal probabilities. So 2/3 times 3/8 is indeed a quarter. And you have to do that for all the cells. So that shows independence. Now, independence does imply that these conditional probabilities must all be the same as the unconditional probability, and this is something that you can confirm. So I calculated it here. So the probability that x is 0 given that y is 0 is 3/8, and the probability that x is 0 given that y is 1 is also 3/8. So, but you don't even have to do this. Once you confirm that x and y are independent, then B is equivalent to that independence. Great. So C is true here. And then we ended. So we want to look at the sum of two random variables. So let's say that x1 is binomial and x2 is also another binomial, and these are independent, let's say. So you can think of, I'm flipping a coin 100 times, and I'm flipping that same coin another 200 times. Then the sum is like flipping a coin 3,000 times. And so what you see is that you get a binomial. The sum of two independent binomials is binomial. And in fact, these binomials are approximately Poissons. So you can see that the sum of two independent Poissons is Poisson, something that we will actually